Dr. Yanping Ma. I hope I actually pronounced rightly. So I excuse before if I actually did mispronunciation. So Dr. Yanping Ma is an associate research professor at a State Key Laboratory of Polymer Physics and Chemistry, Institute of Chemistry, Chinese Academy of Sciences, China. She obtained her PhD in chemistry in 2007 from the same institute. Her research interests include ab initio theoretical study of polymerization reaction mechanisms, electronic and optical properties, and intramolecular interactions in functional polymers, atomic molecular dynamics simulations on transport mechanism in polyimides membranes. So please welcome Dr. Yanping Ma. Yes, over to you. Just please share your screen and start your talk.
Thank you. Can you hear me clearly?
Yes, we can see and also hear you very clearly. Thank you.
Okay. Good afternoon, everyone. Thank you for you give me this opportunity. It's my pleasure to give. So in the introduction, introduce me as the theoretical calculations. But now I will introduce the research progress from our group. The focus will on the later transition metal catalysts. And by these catalysts, we use it for the ethylene polymerizations. So for the polyolefins, they affect all the area of human lives and activities. Here I show some photos here, but it's not limited just this. So this picture is related to the plastics. This photo is reported by the Reuters in the 2018. They reported that in the death whale, in its stomach, they found 6 kilograms of plastic. So the people complain that it is the plastic that caused the death. It's the plastic causing the death. It's true, it's a problem, but it's not all the facts. It's not just a plastic issue. When the whale comes to the island nearby, it is. I think, in my opinion, it's because the food, the fish available, is not enough for the whale in the ocean. So I don't know the reason why the slide is so further to the next. Sorry about this. So everything has everything is two-edged swords. It has positive and negative effects. So another issue about the plastic problem, it is the living people who deposit the plastic without regulations and do not haven't considered about recycling. So in the beginning of my report, I will spend several minutes to the importance of the plastic. If we open the website for the United Nations, we can find for the substantial development, there listed 17 goals. But I will not go detail in this. I highlight some of them, which using the plastic or polymer materials. Taking the zero hunger example, it seems that the people will have enough food. So here, for one person's weekly consumption of food, the energy cost from the food supplying to the finally to the table, the energy cost, the food producing will occupy 51%. In the following packaging, it's shared 10%. So indeed, the plastic is important. If without the packaging, it will cause food waste. So without the packaging, the food waste the food waste will release 350 gram carbon dioxide. If we use the package, the carbon dioxide weekly from the food is just 70 grams. It is 5 times different here. So the plastic really important, and it protects the environment by reducing the carbon dioxide emissions. If we take the commonly cucumber example, if we without packaging, the cucumber will lose water and decompose and go fast to food waste. So the plastic can help people to a good living standards. So now I will go on to my topic. Yeah, it's focused on the later transition metal catalysis. And by this catalysis, we can get either the highly linear polyethylenes or the highly branched polyethylenes. For the polyolefins, the catalysis is the core. That means it's a key point. By tuning the steric effect and the electronic effect, we can design the ligand for the catalyst. Thereby, the microstructure of the producing polyolefins can be tuned by the ligand design, and also by changing the mantle type, the co-catalyzed type and amount, and also by optimizing the reaction conditions. Besides this experimental research work, we also do simulation works by the machine learning and also the density functional theory methods. By these methods, we can construct the structure and the property relationships, and also explain and support the experimental results. In the ligand designs, we develop a new methodology. In this new methodology, we develop the new catalyst, the ruthenium catalyst. By this catalyst, we can catalyze the very cheap sources to the cyclid pyridine-based ligands. Here is the list about what kinds of ligands we can synthesize by these methods. I will not go in detail here, but I will take an example. Yeah, by this ruthenium catalysis, we can get the seven numbered rings fused pyridine, and also the other side by 6 numbered rings. In the ligand designing, we also designed other kinds of ligands. Especially in these ligands, this ligand is expansive, so it synthesizes by itself. But during synthesis, we found another kind of ligands like this. It has ester groups. When we react this chemical with the anilines, we got the ligand is ready for the catalyst. This ligand is special. It can react with with iron, cobalt, nickel, and palladium metal dichloride metal salt. It's interesting to find that if we use the iron catalyst, we get highly linear products. If we use the nickel catalyst, we get highly branched polyethylenes. It's interesting. Just by the same ligands, just the mantle is different. We get totally different polyethylenes. So the next part we will go in detail for these two polyethylenes. So the next part I will introduce the highly linear polyethylenes. In this part, I will mainly focus on iron catalyst. Based on the skeleton structure reported by the Bruhat and Gibson in their early work, we developed many kinds of iron catalyst. Especially, I highlight here for the ring-fused catalyst. The ring fuse can be 5 to 8 membered rings and can be from one side and from both sides. It's an interesting catalyst. We also developed the catalyst with conjugated pyridine ligands. By this catalyst, the activity is high, but the products have low molecule weight. It's oligomers. Even it is unexpected, but the oligomers is good. So we can see it 99%. We can get good results here. Actually, this kind of ligands is hard for the synthesis. It's not easy. We conduct this work, and also the professor from UK, Professor Solon, also conduct this work. But fortunately, we have the past publications here. You will be considering the sources for the synthesis. The potassium cyanide used here is not available at this time in the lab. It is very toxic. But at that time, we use kilograms of potassium cyanide to get just several grams of products. So we develop another synthesis route, a new synthesis route. By this synthesis method, it is more easily conductive and more simple and more cheaper. And we can get several kilograms catalyzed. And the catalyst can also be scaled up to hundreds of kilograms catalyzed. It's a must for the pilot process. So by this, the catalyst was scaled up to 500-ton pilot process. It can catalyze the ethylene polymerizations to producing alpha olefins by the iron catalyst. Now it is going to have the 50,000 tons for the industrial process. Maybe you do not work on this, but in Asia, there wasn't manufacturers working on the alpha olefins by the ethylene polymerizations. Maybe next year, it can happen in China. So it's interesting here. It is also the first time for the iron catalyst used in the petrochemistry, in the petro industry. Another catalyst I highlight here is the 7-membered ring fused to the pyridine center from both sides. By this catalyst, we can get highly linear vinyl polyethylenes, and the molecular weight is low, and the molecular weight distribution is narrow. This kind of material can have potential to be used for the polyethylene wax. Here we can easily buy the proton and carbon AMR to evidence the existence for the vinyl ending group. So since it is potential, we tried to make a bit scale up. It's interesting to find that during scale up, the activity is higher than previous, and the molecular weight keep thousands, and the molecular weight distribution keep narrow. So maybe this kind of catalyst and the polymers can be ready for further petro process. So by the ligand design and the catalyst design, we can get the polyethylenes with various molecular weights. That means we can choose the microstructure of the polyethylene by the catalyst design. So the polymer ethylenes with various molecular weights can be used in different areas. We summarize our iron and cobalt catalysts for the ethylene reactivities in our recent review articles. So now I will turn to our next part for the highly bronze polyethylenes. In the film, they always use the elastic materials for the phase emulation as the phase emulation materials. It's a technical combination of the elastic material and the 3-dimension print and also the emulation techniques. But the commercial and the often used elastomers are the polyolefin elastomers. It is prepared by the co-polymerizations from the ethylene and the alpha ethylene. It's co-polymerizations by the metallizing catalyst. However, in our group, we can get the highly bronze polyethylenes. It also has elastic properties, but these elastic properties, polyethylene materials just prepared from the pure ethylene, just by the pure ethylene polymerizations. It's catalyzed by the nickel catalyst. Professor Zhibin Yan from Canada, he reported the morphology of various kinds of the highly bronze polyethylenes. He used the palladium as the catalyst. In our group, we developed the nickel catalyst by the ligand designing. The thermal stability and the activity has been improved a lot. In the catalyst designing, we also designed the ligand by the ring fuse to the pyridine center based on our earlier reported catalyst. So in the analysis of the producing polyethylene for the highly branched one, we found that for the branches is not a single one. It can be short and can also be long. It contains such as the methyl group and also the ethyl, propyl, butyl branches. So it comes the question, why the iron catalyst can get the highly linear polyethylenes, and the nickel catalyst gets the highly branched polyethylenes. We propose the mechanic about the nickel promoted ethylene polymerizations. We think that the intermediate here is very important for the highly branched polyethylenes. Here the intermediate, the beta hydrogens, interact with the nickel metal center by the agostic interactions. It's interesting. Here the hydrogen could be the beta hydrogen and also could be the gamma or higher linear the hydrogen to interact with the nickel metal center. And by this way, we can produce the different kinds of branches in the branched polyethylenes. Here I show an example for the ethylene polymerization in our group. The reactor is just 250 milliliters. And the activity is high. We get several grams of products here. When we scale up this processor by connecting 3-meter reactors here, after 12 hours, we get the products. It accounts to several kilograms, and the activity is higher than the experimental result in our group, and the molecule weight is higher, and the distribution is good. When we further designed our ligand, such as, for example, when we changing the substitute group from small to higher steric groups, we can get ultra high molecule weight. It is 3 million gram per mole. Since the branch polyethylene in our group also have elastic properties, how about it? We compared the mechanical properties of the producing highly branched polyethylene with the commercial polyethylene with the commercial polyolefin elastomers. We found the mechanical properties is almost equally. You can see clearly here. From this photo, we put our sample in the textile machine. Initially, just a small sample here. When we elongation to 25 times, it haven't broken. So it's indicating that the elastomer properties is good. It's very nice. So in this part, we also summarize our nickel catalyzed progress in our recent review articles. In the review articles, we also designed other kinds of ligands structure. Besides the iron and nickel catalyzed, we also have overall consideration of the ethylene polymerizations, such as the titanium family catalyzed. We summarize all the other transition metal catalyzed in our recent review articles, such as titanium family catalyzed and also vanadium catalyzed, the chromium catalyzed, and also for the bimetal catalyzed for the ethylene polymerizations. I will not go in detail for the other parts. Besides the catalyzed design and the microstructure of the producing polyethylene, we also think about the degradable properties of the polyolefins. We provide samples to the groups who did expert work in this area. We found that the bacteria in the polyolefins with low molecular weight can grow up more fast. That means the polyolefins with low molecular weight can have the degradable properties. So in summary, in our research work, we focus on the later transition metal catalyzed, and these kinds of catalyzed can be easily prepared and stored, and they have highly catalytic activities. And by these catalyzed, especially by the iron and copper catalyzed, we can get highly linear polyethylenes. Also can get highly linear polyethylene with the vinyl ending groups. By the nickel catalyzed, we can get highly blunt polyethylenes. It's exciting that by our iron catalyzed, we have proceed to the industrial process for the alpha olefins. So here, I'm very thankful to our group leader, Professor Wenhua Sun. Under his leadership, we make great progress on this area, on the catalyzed design and also for the producing polyethylene properties. So here is the total result research from our group. Finally, I provide one photo. This photo is taken in last year's graduation ceremony. Here, this is Professor Sun, and it is Professor Zhang, and it's me, and here is Dr. Yang. And besides the Chinese student in our group, we also have postdoctor, this is from India, and also have other international students. Especially, we have 3 or more Pakistan students. So thank you for your kind attention.
Thank you very much, Professor Yanping Ma. So it was very nice and informative talk. And now the talk is open for questions. Yes, Muhammad Iqbal. Yes, please.
Yeah.
Thank you so much for a very, very nice presentation. I just have a question. Do you always work with polyolefins, or you have a plan to work with some step growth polymers like polyesters, for example? Do you guys work in this area as well? In the same?
The mainly is polyolefins.
Yeah, because there are a lot of new polymers coming in polyester family, and people are really looking for biodegradable options for polyester. So I was just wondering if the state clean laboratory is also shifting their work towards polyesters as well.
you can see the plot.
Okay.
The width is not.
Could you repeat the question, please?
I was just saying that there are a lot of new polymers coming in polyester family, or in step-growth polymers, and I was wondering if you guys have a plan to shift, into polyester family, producing polyesters from like biodegradable polyesters from environmental gases, just like CO2, for example, or CO, and developing catalysts for those polyesters.
So yeah, but the catalyst used here we haven't considered for other, because the experimental part is not mainly by me, so maybe I'm not the expert.
Okay, no, it's okay. No problem. Thank you.
Okay. So, any other questions? So, any questions so far? So we still have a chance for last question. We have one last minute. So if there is no question, then we thanks our speaker once again. Thank you very much, Professor Yanping Ma, for your very nice talk. And there are at least some comments about your talk from the participants, and I'm sure that they will contact you for more questions. So thank you very much. Now we move to the next talk. Thank you. So could you please stop your screen sharing?